In this problem, I'm going to derive one of the most important propositions in number theory and sets theory, and we're going to use this proposition in our later videos, so let's be very careful here. So in this video, I'm going to define the set of rational numbers, but I'm going to start with a set of integers and a set of natural numbers. In fact, every number can be represented or built upon the natural numbers in set theory or in mathematics in general. So if we have the set of natural numbers, let's call it the set of numbers starting from 0, 1, 2, 3, 4 until the infinity, because this set is not bounded. And along with that, I'm going to define two more sets. The first set is the positive natural numbers. I'm going to define this as 1, 2, 3 until infinity, and I'm going to define the set of negative natural numbers. These are not the natural numbers, these are just the inverse, with a different sign, like negated numbers. I'm not sure how to call that. Negative numbers, negative natural numbers, just negative natural numbers. So from negative infinity, -2, -1, and so on. So this is negative natural numbers. These are not natural in traditional sense. It's not natural. So since we defined these natural numbers, we can now proceed with the integer numbers. So we can define the integer numbers as z upper, as the natural numbers union negative of natural numbers. So this is going to be the integer numbers. I'm not going to dive into all the intricacies and axiomatic definition of what it is and the isomorphism type of thing and everything. I'm not going to dive deep into this structure. I'm just going to define pretty simple definition of natural numbers and z upper, which is the integer numbers. All right, so how does it have to do with the rational numbers? Well, in fact, the set of rational numbers is introduced a little bit later, and the set of rational numbers is, it is like in its traditional form, it is just the set of fractions a, b, where a belongs to the set of integers and b belongs to the set of positive natural numbers. So this is like saying, hey, we now have integers and we now have defined the natural numbers, so let's go ahead and define the rational numbers, because that's exactly what we can do, right? This is just the fractions, and the fractions are studied in primary school. I mean, everybody's familiar with this subject. So, and that's something that people, commonly study in primary school, and then later they know about, irrational numbers like square root of 2, square root of 3. And in fact, we cannot introduce real numbers without understanding the underlying subject of what natural numbers and what rational numbers, what integers are about. I mean, that's like the baseline that you have to be familiar with, and that's why there is some sort of linear progression. When you go to the school, you study first with natural numbers, you study natural numbers, and you go to the integers, and then you have some linear progression, very gradual progression from simple objects into more complex and more complex objects. So that's why I'm following pretty much the same approach here. I first define the natural numbers, and then I'm moving forward. So now that we have established or gave the definition for the rational numbers, I'm going to introduce its canonical form, because there is a canonical form. So what is the canonical form of rational numbers? So the canonical form of rational numbers, it is like the representation, the specific representation of rational numbers. But to begin with, I would like to get started with the simple fractions. Everyone knows what the simple fraction is. The simple fraction is like saying the 5/15, it is kind of the same thing as 1/3, right? It's just two numbers. So in fact, that 1/3, it has many different representations. It can be 5/15, it can be also like 15/45, and so on and on and on. So I mean, there are lots of infinite number of different representations. And following the same kind of logic, we can apply, to rational numbers, because rational numbers and the set of rational numbers can have different representations depending on what kind of representation for fractions we apply. Now, if we, decide to treat them like, we can use different representations here. We can use the 5/15, we can use 15/45, and so on. But fundamental definition of a set is that we cannot have two same numbers, right? If we already included 1/3, we cannot add 5/15 in the same set. It would be impossible, because is consisting of distinct elements. And we're going to use this axiomatic like definition of the set. This is the axiomatic definition. This is just something that doesn't have like a logical justification within the framework of the set theory, but it is something that we're going to rely upon here. And since we only can have one distinct definition, one distinct representation of a single number, of a distinct number in a set of rational numbers, so let's use the most simplest form. And now let's take a look. Let's rewind for a moment and take a look at these fractions. We have three fractions here: 5 over 15. We have 1 over 3 and 15 over 45. So one can notice that 1 over 3 is actually irreducible. Meanwhile, 15 over 45 and 5 over 15, they can be reduced to 1 over 3. Sooner or later, they can be reduced to 1 over 3 by continuous, reductions or steps of reductions. I mean, that's the basic fact about fractions. So let's just use this irreducible fraction as the canonical representation of numbers, and then we can use this canonical representation for giving the canonical representation for rational numbers and for the set of rational numbers. So we can say that set of rational numbers is by definition, by canonical definition, and this is the exact definition when we are going to use from this moment on in our later episodes, because, well, this is the most useful and convenient representation to work with. So we're going to use it. We're going to say that this is the numbers p over q. I'm going to use different letters, but that's pretty much the same thing, where the p belongs to the set of integers, conjunction q. It is kind of the positive natural numbers. And one more thing here is that conjunction, the greatest common divisor of p and q equals to 1. And this is like the, another way of saying they are not reducible. So they are irreducible essentially, because if their greatest common divisor is 1, there is no common term. We cannot decompose them into into like the product of different numbers with a common term and then reduce them later, right? So if p and q, they don't have the common divisor, then the p over q is irreducible. For example, 15 and 45, they do have the common divisor, which is the 15 here, and the greatest common divisor of 5 on 15, it is also 5, but the greatest common divisor of 1 and 3, it is 1. So this is the canonical form. This is the canonical representation of rational numbers, and we're going to use this canonical representations in our future videos and our future episodes. And one of the problems that I'm going to prove in my next video is the problem that for any element from set of rational numbers, there is always such canonical representation. And this is, so far in this video, we have defined that this canonical definition, but in our next episode, we're going to prove that this definition actually exists and makes sense in the context of mathematical framework, in the context of set theory and arithmetic.